Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, who got the message about the first assignment? You get a Wattle Digest? I've been told the Wattle Digests aren't working properly. But if you haven't been reading the discussion forum or the question or the course announcements thing, you probably should monitor both of those. Though you wouldn't believe the number of questions I get asked by people who obviously haven't read either of them. You know, if you're actually doing this course, please just pay attention. The assignment's due on the 31st. The day before that, we'll have a couple of hours online quiz. If you don't do the quiz is optional. Then the assignment will be worth 20%. If you do the quiz and you do slightly better on the quiz and you get the assignment, then you get the 5% on the quiz and 15% on the assignment. Okay, who's read the assignment specs already? There's a lot of fine print there. Any questions? I'm sure there's some pretty obvious ones at some stage. Most things with me are somewhere in writing. You can probably find out for yourself with a little effort on your part. Sending me an email is a lazy option. To be blunt, wastes my time when you could have been wasting yours. Okay, where we're up to, we're not up to there by any means, that's about 8 weeks ahead. Week 9, sorry. We've been doing the analysis and Ancover models, which are experimental design models. These are just plain, ordinary linear models, sort of stuff that we squeeze into regression modeling if we have time at the end. We wrote these two courses back in the 90s, the bulk of them. I think we decided we were going to try and squeeze the analysis and experimental design stuff into the end of the regression modeling course. It comes in GLMs because the idea of introducing indicator variables, categorical variables, the obvious place to go is on the right-hand side of the model first. When we get to GLMs, we can see we can also put these categorical variables on the left-hand side, but that's tomorrow's lecture. Okay, for today what I want to do is I want to quickly finish off some more stuff on random effects, and then we'll have a look at the analysis of covariance models, which are a completely separate class of models, but just a simple extension to the one we've already looked at. In fact, all the above are simple extensions to the basic one-way ANOVA model we looked at first. Okay, and then tomorrow we'll start on these. So if you haven't started reading this or started doing a little bit wider reading, now is the time to do it. Okay, so this is a bit challenging without any reading glasses. We'll see how we go. As you can tell, I'm running a little bit behind because I was hoping to be, that's the lecture that ended on Tuesday last week. So I'm playing a little catch up at the moment. Okay, so we saw just a single model that had a single random effect in it last week. That actually happens almost none of the time, because typically a random effect is a source of random unwanted variation you don't want in your main comparison. You want to account for it elsewhere. You want to put it into the variance part of the model and get rid of it, because really what you're interested in is the main comparison between the fixed effects. In the experimental design, they're the things you design the experiment to sort of change or to hold at certain levels, and then see what happens to Y, the response. random effect is just some known but unwanted source of random variability. So typically what we do is we take the standard linear model, or the standard analysis of variance model, and we augment it to account for these random effects. We add them in. So if you like, there's the standard regression model from regression modelling. In matrix form looks like that. One of the reasons we use matrices is because the matrix algebra is so much nicer and simpler. It's a shorthand version for a lot of things going on in the background. In the ordinary regression model, all the betas are said to be fixed effects. The only random effect in that is the error term. The error variance is our ordinary variance component so far. A mixed effects model introduces additional random elements to the model. In other words, we have a whole bunch of new things in here which we're going to call random effects. And I apologise for the notation here. I'm not sure. I didn't do this slide originally. I can't remember if I did. Possibly haven't. But really, these B's aren't sampled things, and those random variables, in this case they're all random variables, as the small case ones are the coefficients for the random effects. Okay, and the Z's, well, it's not because they're normally distributed indicator variables, it's because they're just a different way to distinguish from the X's. Okay. What we're going to have, though, is each of these ones is going to have its own variance component. So what's become something more complicated is the variance part of the model. It's not just a single sigma squared for the error variance. We're going to have a sigma squared associated with each of these terms, these additional terms. Each of these other random effects that go into the model. And generally, well, usually to start off with, we assume that the random effects for the sort of the known sources of random and unwanted variability have their own variance components. Here we use a different Greek letter to show them. Typically I'd use sigma with some sort of subscript. And then you've got the overall leftover residual random variation. And yes, those can be correlated, but typically we'll assume that they're independent and we'll estimate them separately. The trouble is, the whole setup's become instantly more complicated when we do this. The way we have to estimate these things is to get the initial estimate for these, hold them constant.
Question about the random variable part.
Yeah.
Is it on average equal to zero expected value, or is it zero?
Yes, well that's what it says. So essentially we assume that sort of the random effect is some deviations away from zero. And we typically do that if they're not, if they're obviously not, we typically do that by estimating some mere effect to get them off first, or we center them, we use mean-centered variables. Okay, so there are tricks to get around these things. Typically, let's face it, I'm not going to get too far into this sort of stuff. This is always an additional section of this weekly course. The trouble is, when you get real data, it's going to come with all these sorts of complications. Okay, that's where the point is to start reading the geometry text seriously, because that's when you need. Okay. For this handwriting, sort of let's get rid of random effects in one lecture. We're going to assume that they're nice and simple, that they're zero-centered. But all we have to worry about is the variance component associated with that random effect. And typically we do this by setting up some initial estimate for those, then we estimate the model, possibly by least squares, then we come back and re-estimate those, holding that constant, and it's an iterative process. And it's done by a thing called Dremel, which stands for restricted maximum likelihood, rather than by least squares. Because it's an approximate method, if we estimate some of our old methods, of old models using Dremel, we could get slightly different answers. Typically, Dremel will converge to what used to be the ordinary squares ones, except in very highly unusual situations. So, most of the time, Remember, will give us exactly what we used to have. When are these models used? Well, most of the time, if you just bang a random effect into a model we've already got, in fact, the old fixed effects models will actually take it down very well. It doesn't matter whether you declare the known but unwanted source of variability as fixed or random, as we'll see in a second. Okay. What it'll do is the old fixed effects models will quite happily estimate some sort of variance component, it will run the analysis of variance table, it will take it out of the sigma squared, it will deal with it quite happily. However, when you really do need to worry about random effects, a bit like when you have to worry about multiple comparisons, it's already when you're starting to get into complicated situations where the situation is not what we're used to. And that's often repeated measure situation. We're doing some longitudinal study, we're analysing longitudinal survey data, the stuff from Hilda, which a few people have done as projects for me over the years. Then you probably do have to worry about different random effects occurring at different time points. Each one will come with its own essential set of random effects. The other situation was the one I was describing last week, where maybe you have a hierarchical model. You're looking at modelling school children within classes, within age groups, within classes, within age groups, within schools, within states. And you may have different random effects that occur at each of the different levels of the hierarchy. Okay. Now, we're not going to get to those sort of complicated data structures in this course. However, sometimes the data becomes that complicated. And then that's when you have to start worrying about these things seriously. Okay, so let's have a look at what actually happens with random effects. The initial estimation of them is actually fairly simple. It's just a matter of calling a different thing in R rather than the thing we normally use. Okay, so I've added a few instructions at the top of here about how to try and set up libraries if you can't. Hopefully, you're in a situation where you've managed to load the libraries quite happily. There's a few hints on how you do it there. What I'm going to look at first is some data on a fairly simple experiment, which was a paired experiment. Sort of thing that you would have had a look at in a first year course. Essentially, each of these 12 subjects are the same 12 subjects. One time, this is played at random, they were given a placebo, the other time they were given an active treatment. Okay? And then their cholesterol was measured after each of the treatments. Okay? Very simple experiment. And obviously there's a pairing between subjects. The subjects here really aren't what we're interested in, are we? We're interested in whether the active treatment makes a difference in the cholesterol levels. What subjects are known but unwanted source of variability. In fact, they are a classic example of a blocking variable. A variable we block and we do the experiment within blocks. Okay, so we should do the comparison within subjects. If we did it in first year, we'll probably have a look at the difference for their cholesterol level for the placebo versus the epinephrine. I think it's actually for some of the their cholesterol, to be honest. So we do the difference between, say, that, and look at it within subject. And we do a paired difference t-test on the differences. That's how we're going in the first year. Now we definitely have to account for these differences between subjects. So what's the first thing I do? The first thing I do is ignore the difference between subjects. I'm going to set up some contrasts. The idea being, well, actually, probably a treatment contrast would have worked quite happily here. I'm only interested in what's happening to the treatment versus the control, which is the placebo group. On placebos, by the way, you've all heard of the placebo effect, haven't you? The idea that people actually get better because you just actually pay them some attention. If you give them a sugar pill, then there's actually a known placebo effect there that haven't given them nothing at all. Well, we ignore that for the moment because we don't have the measurements of no pill. All we've got is the placebo, which presumably should give them no effect whatsoever, and the active treatment, which should give them some sort of effect. So the first thing I'm doing is going to fit this model, and this model actively ignores subjects by not having subject in the model at all. Okay, so all it should do is going to compare the mean for the placebo group with the mean for the active treatment group. It's going to be an independent samples test on the difference between the two means of the two groups.
Do you do anything with regards to the assumption of independence from the same subject?
Well, I mean, the assumption of independence is wrong in the sense that they're not going to be independent. We've actually just ignored all the structure there is here. So that model's wrong. On trying to face it, the model's wrong. Here's the way you probably would have done this for most of my academic career. You'd have treated subject as a known source of variability. You didn't want any comparison, and you wanted control for it. Okay? So it's subject as a series of factor variables. All we have to do to treat subject as a random effect, well, we have to actually call a different library, because essentially the standard R doesn't come with this particular bit. And we're now going to use linear mixed effects, which is from the NLME library. And we're going to set it up so that we have essentially the base model, the model we used first, but we're going to basically sort of say that there's random variations, and we're going to allow random intercepts for the different subjects. Okay? The way you read this is within intercept, you allow differences for the subjects. You were asking me the other day about what happens if they have treatment, and you have treatment within that subject. That's allowing different slopes as well. Okay? Okay, but again, we're not going to get that complicated here. That would be sort of basically assuming that there was correlation between the blocks and the treatments. Yeah. If we're just assuming independent, the usual thing is all we're sort of saying is that if you have a different intercept for each of the different subjects, they all have a different level, if you like, and that level just moves up and down, but the effect of the active treatment compared to the placebo will be constant, for each subject. It will depend on which subject you're dealing with. And here's a more recent attempt at the same thing. It involves a slightly more yes, who knows if that's actually worked. Let's see if we can actually fit this. Well, nice if I fit the whole thing. Yeah, I can't find LMER. Okay, so let's just quickly see if my little here was what I suggested you should have to do if you oh, that's the wrong one. No wonder it ran quickly. That's what he comes with standard R. So the one we got a message about it not being there seems to actually be loaded now. Okay, so this is going to take a little bit of time because it's a fairly big package from memory, this one. So if you're using a sort of a vanilla version of R that you download for your own computer, then this is probably the way you have to install, one of the ways you can install packages. There's actually a couple of different ways you can do these things. I suspect me teaching you how to do flexible computers is probably a bit like a dinosaur or teaching how to do it. I do have a degree in computer science, but it was done on card punchers and card readers. And all else found shufflable cards. Never worked. The option command. Oh, the options command is to change various parameters. So there's various default parameters set in R, and getting into those and opening them up and changing them is one of the more complicated bits of R. So you can actually see what options are currently set for yourself by going options with just the two open brackets. And it will read you through all the options that are set by default. That includes the contrast options and a whole bunch of things. Okay. So all I did with the options command there was I set it so that the defaults are now no longer treatment contrasts, because the contrasts are now some contrasts. Okay, so. If I speak up or look at me carefully and tell us what it is. Okay, we'll read this one. Oh, the order command. Well, the order, like any command you don't understand, going in help order actually is quite useful. Order will do different things on different objects. What it typically will do is just see the scale of the numbers in your order, in descending order. Okay. But typically, if you don't understand what any of these things are doing, look at the help file as a good idea. The trouble is that when you asked me about the options command, help options command is written in computer gobbledygook as opposed to written in English. So it's not necessarily helpful. If you're having trouble with those sorts of things, those sort of nitty-gritty are, that's a good thing to ask the tutors in the Consulting Times or YouTube. The computer in front of you, you can basically go through and sort of experiment a bit. One of the best ways to experiment the help files is to look at the bit of example code at the bottom of the help file and run that. Most of those run on data sets that come in standard R, and they will just run as they are. And you can see what they do. Okay, we should be able to do this now, hopefully. So let's try loading the library again. We get a different set of red warning messages now. And do we get? Yes, we got success. We managed to run it. I always love the way that when I first studied command languages, the fact that it just came back with a blank cursor was a real one. Okay. So I've actually just finished 4 models here. And both of the last 2 purport to allow random variation between subjects and do it by basically modifying the inset at random for that subject. So again, there's a hint about here, seeing help LME and the various help files, which won't work until you've loaded the libraries. But again, once you've got the libraries loaded, you should be able to get at least a usable help file on that. So essentially, the whole idea is for the different statisticians you contribute to R. When you contribute a package to R, you have to basically have help files, you have to have everything in there. So all the parameters of R should exist for anything that you can load from a library. And like I said, down the bottom here, there's some example code, and that probably should work on the standard stuff that's available in R. Okay, so let's have a look at the output. Well, let's first of all look at the plots, because we should do things in the right order. So here's the plot for our basically just a model involving treatments, ignoring subjects completely. And what do we see? Well, we see a mean for one of the for the active treatment and a mean for the placebo. I think it's that way around. And you just see 2 columns of 12 numbers, because that's what we've got. We've got 12 observations of each. And essentially, like anything, it's fitted. The model it's fitted is basically connects the means of the 2 groups. Because really, the thing you're interested in here is, do those means differ? On inspection, it looks like those means don't differ. You've got pretty much very similar groups, and they're not going to differ at all. Of course, you get all the other plots with this one. You get a normal quantile plot, which with 24 observations doesn't look too bad. The one I never talk about, and that one, which of course, because it's safe. It's saying here's the ethylene group, here's the placebo group, and there's the model. Standardized residuals, no real problems there, no outliers. Okay. What do I get for plot.cholesterol LM1? This had a factor subject included in there, fixed effect for subjects. Well, okay, now, subject variability spread things out a bit. We're seeing what's more like a residual plot for a model. And if we get the median smooth when it starts behaving like that, it's basically pretty well close to the model. The model's the axis line here. So no real problems there. Normality is about much the same as it was before. And again, we see that. And again, an artifact. He's now give the claims because he wants to ignore it. Okay, and if you do the new LME models, they give you one plot and one plot only. It doesn't look much dissimilar from the. If you go back to the plot we had for the, it's a standardised plot, which is nice. But if we go back to the, it actually looks like that plot drawn slightly differently. Okay. And that's all you'll get for the LMER one as well. Again, very similar. So all of them seem to say, look, this is an appropriate model, there's nothing wrong with these models. We know there's something wrong with the first model because we know it ignores some unavailable information. Let's have a look at what the analysis of variance tables tell us. Because that's where we should go first with any experimental design model. We should go and see which are the important terms of the model before we start trying to tease out what is there a treatment effect if we ignore the effect of subjects? No. If we include subjects, and there's a lot of difference between subjects, then there is an important treatment effect. Notice the mean square is exactly the same. What's changed is the error mean square. Because we've taken out a variance component due to subjects, we've reduced this down so that this divided by this is now large. Okay? So that's how that fixed effects model is actually controlled for the difference between subjects. But controlled in such a way that we now actually have a comparison between the two, between the treatment and the active, with the active treatment and the placebo treatment. Here's the LMER one. Notice it gives us almost identical results to this one here, without the p-values, because whoever wrote this between the R doesn't like p-values. And I mean, I can't see the point of not giving you a p-value for that. They're 18 on 1, and it doesn't give you the residual degrees of freedom, so it's kind of hard to calculate your own p-value. I think we're just being lazy. It's got a large F value, it's going to be significant. What's happened to the subjects here? Well, because we treated it as a random effect rather than a fixed effect, it's no longer part of the mean model. It's not treated as a term of the mean model in this layout. I'm not sure that's a great way to do things. I should still be a term in the main model, because it's a term in the model, and therefore it should determine the analysis of error table. But really what's happened is we've taken out the effects of subjects as a separate random effect. We've taken out, we've accounted for their variance before we did that division to get that F statistic. And not surprisingly, yes, pretty much the same. What about the last one? What's that doing? Again, it's exactly the same. No, that's because I did the same command again. Somebody stop me. Here's the other one. Okay. Now this is the old-fashioned version, the older of the two things, and this one does have p-values. It does have the f value, which is exactly the same for 3 decimal places, and it's also got, notice here, it's actually included the random variation associated with the intercept terms, because we've got random intercepts here, that account for the differences between subjects. It's got a variance term to do with them. Notice it's a little bit different from what we get if we treat it as a fixed effect. There is differences, but it's pretty much accounting for the variation in the same way when it comes to dealing with the main comparison. The main comparison for treatment is pretty much what we had there. So here's the summary. That's 0.6, not staring at the t-value, not surprisingly because that t-value is the square root of the f statistic we saw earlier, because it's really a simple regression model, this one. Here we get, the coefficients we get here are a base intercept and variations of the intercept due to the different subjects, and we get a treatment effect, and we get a treatment effect that's, well, that's 10 to the minus 3, that's 0.0012. And here, I'm not really sure how to interpret that. It's suggesting there are differences. It's probably the square root of the f statistic associated with this. But it's saying there are pretty much the t-value here and t-value there are pretty identical. Oh, that's the LMER one, sorry. I think I must have missed I keep missing the LME one. Oh, the LME. The LME is a bit messy about how it organises these things. It's got, if you like, an intercept, a treatment, and then variations for the intercept for the random effects. And notice it's got 12 of those, so it's worked out the missing one, even though it's done a fixed sum constraint. Okay, let's have a look a bit more detail at the output you get from the two linear mixed effects models. So you notice that it's a linear mixed effect model fit by Remmel, restricted maximum likelihood. It uses its convergence criteria. I think it uses an AIC criteria from memory. Basically, when the AIC doesn't change by much, the key information criteria doesn't change very much, it stops iterating. There essentially is your base model. Well, it's the random effects. So this one is basically the random effect associated with difference between subjects, and that's going to be leftover residual random variation as standard deviations. So if you want them as variance components, as sigma squared, you've got to square both of those. Here's your base model. You've already seen the coefficients for this, with the significant t statistic there. And you've got a bit of a summary of the residuals, and a bit of a summary of the data. Here's the LMER version. It's also fit by Dremel. Probably a slightly revised version of Dremel. And doesn't tell you what the Dremel convergence criteria was, but it tells you how many iterations it took to get there. It's got a quick summary of the residuals. It's got the random effects, and notice those are pretty much the same as the ones we got up here. So 24.461 is slightly more decimal places there, and 2.744. So it's got the same standard deviation components there, and it's got pretty much the same fixed effects. What can we do with these? Well, what we can do is we can at least work out the sigmas. So there's the subject variation effect, the variation due to our random effect. Here's the leftover stuff, worked out as variance components. The total variation that we're therefore dealing with is the sum of those two, and the interest correlation coefficient is basically how important was the inter-subject variation as a proportion of total variation, but it was 98% of what was going on. In other words, it wasn't ignorable. That first model was as plain wrong, because it was ignoring some stuff we should have done. Sometimes it will be ignorable. Do we still block? Do we still account for blocking in our model? Well, because when you think about it, a priori, we designed this experiment with the belief that this block, there was going to be some random variation between blocks that we didn't want in our comparison. And so therefore, the reference model for our experiment is the one that includes the block converter. In other words, we should make reference to that. We should include the blocks even if they're not ignorable. We don't know the final model. Because the model we had in mind when we designed the experiment included blocking in there. Because the part of the experimental design is included blocking. It's allowed us to control for known but unwanted sources of variability. So now we find the blocks out of the model if they're not significant. And typically we don't also include an interaction between blocks and the main subject effects for the same sorts of reason. Because typically we don't, unless you expect those a priori, they're not part of the reference model. So pairing is really the simplest form of blocking, and we should incorporate it into our analysis of the results. Here's a slightly different one, a more complicated one, just to see if we can get some differences between the Dremel estimates and the least squares estimates. So this one is a classic plot and block experiment. We've repeated the experiment essentially 3 times, one from each block. But each experiment involves basically 8 stock and sine rate combinations. So basically these are carrot seeds. Think of the blocks as being a little sort of plot in a greenhouse. And we have basically got T stock and H stock, and we've got different ways of how much we spread out. And then we look at how many carrot plants actually germinated, produced of those. And it could be a weight of carrots in kilos. I'd have to look up the original experiment to answer all those. What we're interested in, obviously, here is what's the optimal stock to use and sign rate to use to maximise the yield. We're not worried about the blocks. The difference between blocks is a known but unwanted source of variability. We think the blocks might vary, so we're going to include them in our experiment. So, the sensible models. Here's a fixed effects model. Notice there's no real reason to presuppose that there might be differences in the different treatments, the different combinations of our experimental variables, so experimental factors for the different blocks. But there's just that there might be a difference between blocks that we can measure, so mean difference between blocks that we can measure. So typically we wouldn't put a star here that would form the three-way interaction, unless there was a sensible reason to do so. Okay. And the same model fixes a random effects model is here. And now we're sort of saying that we're allowing the intercept to vary randomly between blocks. The plots, we get 4 of them for the fixed effects model, which don't look too bad. We get 1 for the, at least it's standardized, for the linear mixed effects model. None of them showing any real problems. The analysis of variance table has, the fixed effects model has components for the, well, okay, it doesn't seem that we have to worry about the combinations of stocks of the same rate, but again, we probably wouldn't remove those. That is probably the model we had in mind when we designed the experiment. So that's the reference model. That's the right estimate of the error mean square. we would probably make our conclusion, draw our conclusions with reference to this model, rather than with reference to a diminished model that included the exclusion action. If we thought it was sensible to allow for this before we started, then we probably should keep it in the model, because it's part of the experimental design. But the answer is, no, it doesn't seem to be important. Notice there doesn't seem to be much difference between the blocks, but it's still sensible to account for any possible differences between the blocks. But there's definitely differences between the different stocks used and the different sewing rates. And then we would go and tie down which one of those is the optimal one for the best yield. That's not the point of this exercise, though. This exercise is to have a look at the coefficients. There's the fixed effects one. There's the linear mixed effects ones. And if you can spot any differences I couldn't when I had a quick look earlier today. I don't like the set out for the second one. But really, the blocks ones, so there's no relationship between those and those. Here they're doing sort of variance effects. There they're set up as fixed effects. They're all not the case because they're not what they're of interest. And the other coefficients are almost identical, even though they need to be estimated by Dremel rather than sort of basically by all these squares. So, the bottom line is, you probably can quite happily deal with the random effect by just including in the model as a fixed effect, so you can include the analysis of variance table. If it's a simple a data set or an experiment with a simple structure. If it's hierarchical or it's repeated measures, okay, you've got more work on your hands. Last but not least, we could work out how important blocking was here. That means we've got to tease out the variance components from here. That's about a half which is about a quarter when you square it. That is 10 to the minus 5. That's got 4 zeros before you get anywhere. When you square that, it's going to have 8 zeros before you get anywhere. Add that to a quarter, it's a negative addition, so the portion of what variability out of the total is minuscule. The relative difference between the plots was nothing compared to the overall. So we didn't really have to worry. We don't have to worry about it, but we wouldn't go and find out of our analysis. Because it was part of the experimental design. Okay, any questions about all that? The whole business about this was that we used to include this in the top of this course to make people aware of the fact that what you're really doing when you're doing blocking and experimental design situation is that you are controlling for known or unwanted sources of variability. These are cloud domain comparison. In fact, there's a lot of things that actually come through in data analysis where you should treat the effect as a random effect, a known source of unwanted variability in making domain comparisons. Something you should try and get out of the variance model before you make domain comparison. Okay, now, in a simple situation, you do that just by doing the effect. You should also be aware if you've got powerful data with different random effects occurring at different levels, then you probably should be doing a little bit more complicated things to account for what you should be treating as random effects. In fact, these days, if you talk to most experimental statisticians, mixed effects models as a point of sort of almost religious fervor. A bit like talking to Basin. Okay. In other words, it's the right thing to do. The correct treatment of these effects here was actually probably the treatment with the LME or the LMER functions rather than the iron function. So the treating is a random effect. Because that's what they really are. Blocking is a known but unwanted source of random variability. On the other hand, I don't like the output from either of those two things, so it's easy to interpret the one from the other function.
We need to use the sum contrast. Is it masks?
Well, we didn't need to use the sum contrast. In fact, in all of this, we actually didn't bother considering what the cartridge was actually meant. Now, if we were going to go on an analysis experiment and try and work out which stop in the station, which stop in the sign rate was the right one, then we probably have to be able to interpret the coefficients of the model. But most of the comparisons we make, it doesn't matter which contrast we use, because the analysis of variance table on the plots vary with which contrast you use. So you don't need to worry about up to that point. In fact, most of the time, what you're interested in really is up to the analysis of variance table. You're just interested in what's the important things in my model. Okay, then how you sort them out? Well, it doesn't matter. Again, you can use some contrast or treatment contrasts. But what you can actually do is work with the group meetings and do the stuff that we. So so if you work with the group meetings, then you basically do that sort of that little trick we did in page 8 of the book, where you just work on linear combinations of the group meetings, and you can work out the right standard error for that linear combination, and then you can use that to make the comparison you want. In other words, you work out what the key comparison is in terms of as a statement of the group means. And it doesn't really matter whether you use some contrast or treatment contrast to implement those. But if you actually want to interpret the coefficients from this table here, you need to know which contrast was used. Because that's answering a question about how much does this sign rate differ from the overall average sign rate? How much does this stop rate differ from the overall average sign rate? And if you want to have a look at sign rate 4, you've got to take the sum of those and take the negative of it. But we have the same standard error because it's a balanced design, and you can also calculate a t-statistic for that. Similarly, you can do the stop 2 by taking the negative of that, but that's because it's some constraints. So some constraint, some contrasts, and that's how some contrasts work. But most of the time, unless I actually get my hands dirty with the coefficients of the model, it doesn't matter which contrasts I use. In some ways, it's probably better just to use the default and then do a custom contrast in terms of the means, the group means you want to compare and contrast. But good question. Okay, any other questions? Okay, well, a 5-minute toilet break, and then we'll go and we're back at 5 o'clock, and we'll do the analysis of covariance in an hour.
I don't understand how if we used a treatment it wouldn't incorporate bias. We used treatment contrast because I thought we used treatment contrast for one of the one of the parts. Like, what if that one that we chose, or what our chooses is like a high or a comparative low value?
Well, it does bias you towards a certain comparison. So, I mean, you know, this is a comparison between this solely rate and the overall average. This is how much you just see that. The difference between the overall average and the sign rate is different. The difference between the overall and the sign rate and the average for the reference to the sign rate. It's smaller. So it's actually comparing two. It's not comparing like with line. You're contrasting what's the difference between this group and the reference group. This is the difference this group and the overall average. So all these groups. So that's why the difference stand there. You can actually work out this just about 2 pages. They all fall out. You set up a contrast set, so you look at a set of means for top groups, and you work out a contrast rate. It's like, well, this plus this, more twice this plus this, and then you put a contrast test, and then you don't actually if you're simple, just like that's really the comparison.
In that example, wouldn't they select one to track the other?
No, the intercept there's two groups of 12, and when you have the overall average, all the four is on the intercept. And then it's going to, you move
back to that car example.
So you
know later
you move to the active treatment, and then placebo. So alternatively, you can call the placebo or zero treatment, and then you move from the insect the active placebo, and the difference will be expressed as the difference between the two groups. That's the contrast to use in the first one, because that way you get, you get comparison between the two groups. Here, depending on what's got 1 and what's got 2 it's going to be action and saying, well, that's the what's the missing one? Well, last one if it's saying right 3 I don't know the asterisk inside. Well, this is the stuff from, I can't remember, this is the summary from the other email. And because you also this one, it's something like the reference. It's a personal flight. I don't like the reference. I mean, you should have worked out what you're comparing this with. Yeah. I know you is this less than 0.05 or not? Okay, so these ones, a lot of these were less than 0.05, which is consistent with the analysis of those tables. There are no differences between the combinations of stock and stock. Whereas this one is not much different from the overall average. This one is different from the overall average. It's because we've got a second low and so, yes, this one is different from the overall average. What you read the one positive coefficient. Okay, well, I might as well run people through that one. There's some contrasts. Which stock do I want and which sign rate do I want? Should be able to work it out for these coefficients. Okay, there's some contrasts. So, first of all, we knew from the analysis variance table there was no significant combinations of stock and sign rate. And you can see that it's sort of reinforced here when none of these things have a p-value less than 0.05. So in other words, we don't have to worry about combinations of stock and sign rate, but we have to worry about the additive effects of stock and sign rate. So what's the best stock? Stock 1's got a negative coefficient. Stock 2's got a positive coefficient. If I want to increase the yield, I want stock 2. Using the defaults, what's stock 1 and what's stock 2? The two stocks were the H and T. We didn't tell you what we were, but the H and T. So do I want stock T or do I want stock H?
How do you know that stock is positive on the table over there?
Sorry?
How do you know that stock?
Because I use some contrast.
Okay.
And therefore the addition of the two stock levels has to be equal to 0, so it has to be negative that one. So the other one, the stock 2 is the positive one. It's the one that's going to be positive, and it's going to be, this is significantly below the overall average, so the other one is significantly above the overall average. So I want the second stock. Which is the second stock? I know it's 12 o'clock on Monday, but you know it's stock T, because how does our order things for the same contrasts? The default it uses is it fits the first one. It orders them in first of all alphabetical order, H and T. It fits the first one, so that's stock H. And the one that's not fitted is stock T. That's all the positive coefficient. What about the sign rates? Do I want 1, 2, 3, or 4? Well, I don't want 1 or 2 because that one's significantly below. Well, it's not significantly below the overall average, but it's below it. That one's significantly below the overall average. This one is significantly above the overall average. So stock sign rate 3 is looking pretty good at the moment. What about sign rate 4? How do I do? Under some contrasts, I add that plus that plus that, and the missing one to make 0. So that's minus 0.4 minus 0.84 plus 5.2 is about 3 and a bit. So the other one is going to be minus 3 and a bit. The other one is going to be plus 3 and a bit. So in other words, stock 4, which is the most stocking, the highest selling rate, is actually not optimal. Once you get to a certain point, you go to clarity. Stock 3 seems to be optimal. So,
And you have a p-value, you see what how you know it's going to be.
well, I know its p-value is going to be because I can basically, I know what its standard error is going to be because it's a balanced design. The standard error is, I can work out, I can add those 3 together, take the negative of them, it will have the same standard error, because it will follow the same contrast as the other ones. It's just going to have a 1 in a different place. Okay. It will also be on 14 degrees of freedom, which is the only degrees of freedom in all this. And its t-value will be 0.3 divided by 0.19. It will be something less than 2. It probably won't be significant. Okay, that's just by section of those. Okay, so if you've got yourself in a whole bind about sum versus treatment contrasts, and you've thought about helmet contrasts, don't worry too much about those ones. They are important, but they're only important if you actually look at the coefficients and try and work out what the hell's going on. Often it's better to just do your own custom contrast and work out your own the standard error. The else to do is quite simple, or at least the computing you can do is quite simple. It's a simple basic mathematics. I'll show you a couple of examples how to do it. Okay. If you have a sum, by the way, there's only one question you actually got, or you have to actually bother looking at the coefficients. The rest of the time you can ignore them. Okay. The trouble is that the actual coefficients typically are where the answers to the actual research question you've got are hidden. So, yes, sometimes, at some stages you do have to get your hands dirty and look at the coefficients. What I want to do now is I want to move on to analysis of covariance. So, here's the workshop. What we've got here, apart from a major exercise by me last week where I went to try and find out why I got this wrong, was we've got a series of 32 cases. This is the birth weight of new babies in grams, how long the gestation period was, and whether their mother was a smoker or not. Okay, 16 of each. Now, when we have chased down the source, it seems they actually come from the North Carolina birth registry. I suspect these were sampled, so we had 16 in each group. I think even when these original data were taken, there would be less people in the smoking group and smokers were pregnant. Even if we take it sometime in the past, that's the stage. Most women will be warm on the smoke more. Okay, so I suspect these were sampled at random from 16 taken at random from the smokers and 16 taken at random from the non-smokers, probably possibly matched on birth weight to try and sort of sit so they could basically control. And so it's a quasi-experimental design. Okay. If you look at the stuff that's in the newer versions of the same textbook, there's actually 100 cases and they're not balanced. There's a lot less smokers than there are non-smokers. So what do you think the research question is here? Yes, does smoking have an impact on birth weight? The answer is, I'll give you the headline now, it reduces the birth weight of the baby. That might sound a good thing if you're a pregnant woman, but I trust me. I did the National Cancer Statistics for Australia for 5 years. I have nothing good to say about smoking. Before we discuss the other really should give it up. Because the downside of dying from small cell carcinoma for long in about 35 to 40 years is pretty horrendous. Okay. And the other epidemiological studies, which have also come into my sort of bill at times, is show that reduced birth weight is typically associated with a lot of very poor health outcomes. Okay? So, in that sort of sense, the reduction in birth weight we get from smoking while you're pregnant probably also introduces, well, apart from introducing some poisons into your system that are going to be harmful for the baby, they will probably also lead to some of the other complications that come with lower birth weight. Okay, so let's have a look. How do we analyse this data? First of all, birth weight is obviously our response thing here. It's our Y. We've got a categorical yes-no verbal, which is one of the expanding factors. Our other expanding factor is a continuous covariate. It's something that varies along with birth weight, but isn't controlled in any way. We can decide when the baby came out, the baby didn't. Okay. So in that sort of sense, it's random. But it's random in the sense that it's a covariate. Well, okay, I don't want to treat it as a random effect. I probably could treat them as random groups. If I have enough sample in each of the groups. But what I really want to do is treat it as a continuous covariate and include it in the model somehow. So how do I include it in the model? What should I do in the way of exploratory data analysis to start off with? So I might just close this down and get out. And then reopen here so that we can get a brand new workspace. Just in case I create a new object, and I don't want to interfere with my code. Okay, so first of all, the bottom line is that this one's not in the brick because it's a simple example that's in the brick. The brick's an unbalanced design on teacher effectiveness. I'll give you all the data and all the code for that as well. Some other time. It's an update this time, it's actually in the brick. Just another example I thought was a nicer one. Okay. So I'm going to read and attach the data. And I've got those three variables. That is, I've got 60 of each. I've got the summary for birth weight and for gestation. What's the first? Well, I'm going to also separate the data into the smokers and non-smokers, so I can fit separate models for the two groups if I wanted to. What's probably the first thing I should do in the way of plotting these things? Sorry? Well, I mean, a plot of birth weight versus gestation is just going to be two columns, always with half and two. And I want to see how birth weight varies for the continuous covariate. So a plot of birth weight times gestation against gestation. So gestation is the x because it's the expanding factor, and y is the response. Just to see if there's a relationship. Let's do that already. Have I attached the data already? I have. Okay. That's a major bit of typing without my reading glasses. Trying to remember the keys on. Okay. Yes, it looks like there's a relationship between birth weight and gestation. The longer the baby's in the womb, the heavier it comes out typically. So let's have a look at this relationship for the smokers and the non-smokers. So for the smokers, I would have an intercept of this. Is the intercept relevant here? A 0-week gestation baby has a weight of minus 2.4 kilos. It's totally irrelevant. Remember, regression is a linear local approximation, or within the range of the data. There's nothing to sort of say that what's actually happening here is we're seeing a curve in the relationship, and we're just taking a snapshot. It looks roughly linear in the usual range of gestation. Okay? But if you extrapolate that back, it goes to a negative. Okay? So the negative, every additional week of gestation seems to add another 139 grams to the baby. How do we go for smokers, for non-smokers? An even bigger intercept, but an even bigger increase in in birth weight for every additional week of gestation. That's treating the two groups as two separate groups of 16. I don't try and fit a model that basically summarised all my data in one model. So here's the whole lot, and overall, well, it's a bit different, isn't it? In fact, there's not so much between those two. It's actually a little lower, but what it's done is move the intercept up considerably. Let's have a look at that graphically. So we'll start with a blank plot, because I'm just a die-hard Lewis Carroll fan. There's a lot of map in the hunting to start is totally blank on the basis it doesn't do a 3D way. So here's the perfect plot that won't bring the speed to anywhere. Now, let's add in the smokers and their model. Let's add in the non-smokers and their model. And let's add in the overall model for the two groups. What do you notice? You first notice that the non-smoking group is sitting above the smoking group. Typically, for the same period of gestation, the baby's non-smokers are heavier. Okay. So I'm going to fit a model that allows for birth weight on gestation and smoker plus gestation colon smoker. So what's that going to actually allow me to do? What's that model? This model's going to have, if you like, an intercept. What sort of intercept is it going to have? Well, I haven't fiddled with the defaults at all, so it's going to have treatment contrasts. So that means it's going to model one or two groups, and then the other one's going to be deviations from that group. Gestation is basically a yes-no. It's definitely going to be a categorical factor, even though I haven't declared it's a factor. I will know when it sees the two things yet, Y and N. Actually, sorry, smoker. Yes, smoker will be a factor. Yes. Thank you. Gestation will be a continuous covariate because it's numbers. And this will also be a sort of a factor times a covariate. Notice I could have used a shorthand for that. Gestation star smoker would be to tell it to go and fit gestation plus smoker plus the combination. What is the gestation colon smoker going to allow me to do? I'm going to get a slope coefficient for here. I'm going to get an up and down movement in the intercept for here. What's going to happen with this? It's going to allow the slopes to be different for the two groups. It's going to be a change in the slopes for the two groups. So let's have a look at the coefficients. Okay. So, remember, treatment contrasts for the smokers. Who's first? The non-smokers or the smokers? And coded Y and N. What comes first alphabetically? Non-smokers. So, surprise, surprise, the intercept for the overall thing is the same as the intercept for the non-smokers. The slope coefficient for gestation is the non-smoker gestation. Okay? So if you like the base model here, the model for the N category is the same model as we fit into the non-smokers. What's smoker 2 then? It's how much I have to move the intercept to get to the other group. So that plus that equals that. And how much do I have to change the slope to get to the other group? That plus that equals that. So you see how it's modeled in both the two models I had earlier in a single set of coefficients. I could do the same thing with some contrasts. So all I've done now is I've switched the default contrast so that I'm using some. And because it's all balanced, this should all work out quite nicely. If it wasn't balanced, it wouldn't work out nicely. This is the average of those two. This is the average of those two. This is how much I've got to move from there to get to there. Sorry, this plus this is how much I've got to move to get to there. This minus this is there. This plus this gives me that. This minus this gives me that.
I've got a question. The interactions and therefore gestation and smoker, what does that exactly do? I don't follow with that one.
Okay, well, what it's doing is allowing the slope to vary. If we don't have the interaction term in, then all we're saying is all there is, and this is what the graph looks like really, is it looks like the difference is just a parallel difference. Okay, so in fact the change in slope isn't that much. There's a question about whether it's important. So in that sort of sense, what we could do is we could look at the analysis of variance taking the sign of direction mean. We could go with a simple model that just allows a parallel difference between the two groups. Okay. But at the moment, we're allowing a small variation in the slope for the two groups. That's what the interaction term gets me. Here's the summary. These two analysis of various tables are identical. Why? Because it's the only difference between the two models was the difference in the sum contrast versus treatment contrasts. And it shouldn't make a difference, should it? And it doesn't. And there's the answer to your question. We don't really need to allow for different slopes between the two groups. Just a mean difference is going to encapsulate what seems to be going on. Again, remember this is just a linear local approximation to what's going on in that period of full-term values. Really. Now, I think it probably is quasi-experimental, but I treated it just as an observational one. If it was quasi-experimental, I probably would have treated with a model in mind to do things like test for the possibility of the slopes, and I probably would start with that reference model. If it's observational data, which it could equally be, to make a few of the assumptions I've been making the other way around, then I could probably sort of treat this as being sort of optional and treat it just like a regression model we're finding out. In other words, which model fits the data best compared to another model. So, here's a third attempt at the same thing, and the difference is, notice I've gone back to treatment contrasts now, because I think they're slightly easier to interpret here, and the real comparison we're making is between the non-smokers and the smoking group, isn't it? And so that treatment contrast allows you to do that. Okay, and birth weight equals gestation plus smoker, there's no interaction term now. So in other words, I'm forcing a parallel lines model. The two things will have the same slope, just different intercepts. All that's going to happen is they're going to move up and down for the two different groups. So there's the summary. Notice because I used AOV, what I get for the summary is I get the analysis of variance table. If I used OM, I would get the coefficient summary. Typically, with any experimental design, I'm usually really interested in seeing this first. It forces that discipline on me. Now I should check the plots. Notice I've gone to using which equals 1, 2, 4 and 5. Because those are the 4 plots I want to talk about. I'm going to ignore plot 3, which is one of the plots, and I'm going to ignore plot 6. I really do not care about plot 6. And I don't care that much for plot 3 either, so. You don't have to stick with my tastes. As you can see, every person who's written a different bit of R has got their own tastes in these things. Where's the residual plot? Is there a problem? Quite high. It's a wavy red line. Totally ignorable. Want to argue with that one? There's possibly a hint of increasing variance. Yeah. Again, I think it's an artifact more of what done and got in which range of the external range rather than anything else. It wouldn't be sending me out to do a transformation to fix things until as soon as I look at the standardised plot and see about any large portion of my data falling outside plus or minus 2 standard deviations, for instance. The next plot, the normal quantile plot. Relatively small data set, minor departures from the melting. I don't care. Good enough for an observational model. Cook's distance, overall scales relatively low. The worst one's not particularly bad compared to the next one down and so on. I wouldn't be going around declaring observational level an outlier. And there's the residuals versus leverage plot. And the Cook's distance things don't even appear. The Cook's distance limits are off the chart. And you look at the standardized residuals, which is one of the nice things that this plot gives you. Everything's basically, well, there's one maybe that's outside plus or minus 2 standard deviations. I don't think any of this is really low alarm bells at all. I'm sure I need a similar plot in the exam though, it will be alarm bells lots of people. Because it's obviously the point I have, they do exercise some judgment on these things, the hardest thing I have to do all semester. Okay, so that seems okay. Let's go and have a look at the coefficients, because that's where the story lies. So if you like, you can just get the coefficients out by going coef, but that doesn't tell the whole story. Let's have a look at these. So, if you like, the base model is this. Smokers, you have to lower the entire thing about another 245 grams. And it's a big jump. It's got lots of zeros before you get to the first 2. In other words, under this model, the babies of smokers compared to non-smokers weigh 245 grams for the same level of gestation on average. 244.5 grams. So again, I don't think that's the position here. 245 grams would be fine. And how do I know all that's the case? Well, I can remind myself how it's going to treat things over our treatment contrast. It's not going to fit the first level, it's going to fit the second level. And the levels are going to be in that order. It tells me what the levels are. They're going to be N and Y. And so the base model I'm seeing here is the model for non-smokers. The smoker 2 coefficient is for the yes group, the Y group. Notice, in answer to your question there, there's a whole bit about where I fiddle around with the default contrasts. Your question about the contrasts here. There's a bit of code at the end of this one that shows you fiddling, how you can set them and reset them, and the sort of various things you have to do to interrogate. Okay, so we need to document a bit of that, because otherwise we haven't really talked about analysis of covariance in full. So let's go and do a bit of writing, which is going to be really challenging without my reading glasses. So I'm struggling to even find my spot. Here we go. So here's a simple ANCOVA. And ANCOVA stands for analysis of covariance model. So the jargon I've been using is the jargon of experimental design. In experimental design, a fixed experimental factor that you set, that you decide what it is called that. Just that factor, fixed factor. Something that varies along with the response variable that you know you should be accounting for is a covariate. Okay? And so in this sort of sense, the gestation was a covariate, smoker was the fixed factor, yes, no. Now we probably didn't set it, we didn't fix it in advance, like the classic experimental design, you didn't force those to smoke. But we probably did a little bit of classic experimental design that we sampled the non-smoking modes at 16 that matched the sample of the non-smokers, which is similar to those ones. Okay. So it might have been a classic experimental design. It was done by, post rather than pre-setup. So we've got our Yij equals beta naught. Okay, I'm going to use beta naught because actually the last model I fitted was a treatment model, and beta naught is going to be the inset for the zero group. So I'll make this a bit. Plus alpha I plus beta 1 times xij. So, this was the first model I fitted, the one that basically had the interaction term. Notice how I'm using a mix of both regression type terminology for specifying the covariance and the sort of analysis of variance terminology we used to specify the factors. So the factor, so when we start specifying the assumptions first of all, we can tick those off. The EIJs are going to be, as usual, IID, normal 0, sigma squared. Okay, we didn't fit it as a random effect, we fit it as a fixed effect. So the only variance term in this model is the error variance. represents the birth weights. The alpha IJs represents the deviations due to the levels. Now, what levels have we got? Well, I equals 1 and 2. Basically, as we saw when we interrogated the smoker with the levels thing, we found that they were N and Y of the factor smoker. Xij is just a random variable. It represents the covariate gestation. And the gamma i's, like the alpha i's, represents the deviations this time the slope deviations, not the intercept. Due to the levels of smoker. So the same levels, it's the same I. They are different coefficients, which is why they've got a gamma rather than alpha, but they are basically the same I. The subscript, the difference between the levels of smoker is represented by the subscript I. And then J is the 1 to 16 observations for each of the smokers and the non-smokers. Sorry, so J equals 1, 2 up to, it was 16, wasn't it? Let's get this right. Yeah, there was 32 observations in total, wasn't there? So. Yeah, 16. N equals 2 times 16 equals 32. Now, if I use trig and contrast, what are my constraints? So this is why I use beta naught here rather than using mu, because I'm not going to fit the overall mean here, because I'm not going to use treatment constraints. If we're using treatment constraints, what's the constraint? Well, I set the first one to 0 if I use the I defaults. I fit the alpha for the second one. So alpha s exists, alpha n equals 0. Similarly, gamma n equals so what do we get for smoke equals n? the model is Yij, the fitted Yij, is equal to beta naught plus beta 1 times Xij. In other words, the base model is the smoke model. So when I look at just the intercept and the slope related to gestation, what I'm seeing is those coefficients for the no group. Because I know in that situation that is equal to 0, because the alpha n is equal to 0. That's equal to 0, so those two terms drop out. So the fitted model for the no group is just that intercept and that slope. For smoker equals yes, well this time these things up here do exist, so I've got to include them. And that's what we saw in the coefficients. And it becomes even simpler if you basically get rid of injection term. That's what we decided we could do. On the basis it wasn't a quasi experiment, it was an observational one. And we didn't have this model in mind before we started. I'm not sure which is the right assumption. I'd have to go and read Daniel, the reference here. Well, actually, I have to go and trace back the original references that were in the textbook. Because I've read the textbook and it's not up in here for me. The early editions are even less informative than the current ones. In the recent editions, they've also learned a bit about referencing as well. Okay, I'll start talking you through this, but I might come back to it on tomorrow because it's important. It's another thing I used to write out in longhand in front of everybody, but it takes me forever to do it. So here we go. I'll give you a copy of it online. But just think about what's actually happening here. What you can actually model with these encoded models is you can model a whole range of situations. So, if you've got the intercepts are the same or different, if they're different, you're basically allowing deviations up and down for the different intercepts. If you've got no relationship between your covariate and your response, which could happen, you could design the experiment, you find in fact when you get there there's no real relationship, that all you've got is these horizontal lines. All that really matters is the factor difference. Is there a factor difference or isn't there a factor difference? If there's a factor difference, then you need the towers in there. If you don't need the towers in there, you can go back to just a null model, if it's an observational model. Okay? If you've got the slopes, well, there's no slope, same slope, different slopes. If you've got the same slope, that means that basically the really important relationship here is just the one with the covariate, and all the three levels make the same difference. They're all basically at the same level. You know, in our case, that would have been the smokers and the non-smokers had the same birth weights. Here, they differ by some sort of constant. That's called the parallel lines model. You often come across it in this sort of context. And really, what you're trying to decide is which one of these do you need? And the difference is which of these terms do you need in the model? How did we decide that we could go from this to this? We did it by basically doing a hypothesis test on that term. The analysis of variance sort of said that term was superfluous. We can go back to this one, it's a simpler model. So the principal parsimony tells us we can go with the simpler model doesn't involve interaction. And this one here, that typically only happens in certain situations. You know, typically the intercept is not something that usually fit because it allows maximum flexibility when the mark delegates more. And that's typically the case here. Because the intercepts we've got are all negative. They don't mean much in the context of full-term babies. The youngest gestation was about 37 weeks. That's 37 weeks away from zero. The intercept's a long way from the data. Okay. So I'll put all these stuff up overnight, and maybe come back and talk about this tomorrow. And then we'll start the GRN stuff. The whole difference here is we're modelling in this range here. So that's what it's saying is that you know, in the last few weeks we've got this rapid growth. We'll take that back. So if you extrapolate back to zero, I guess you get a negative figure if you're using the model. Really what's happening is this sort of relationship. That model half as well as will allow some flexibility by including the intercepts. So in the intercepts, it's a lower order term. The rule of thumb here is if it's going through any higher order terms, unless there's a good reason not to, you always include all the lower order terms providing a higher term. So you include a linear term, you include the intercept term. You include a quadratic term, you include the linear term and the intercept term. Because the quadratic that either of those two is a very specialised quadratic, and it may not be a good fit for the other. If you fit an interaction term, you fit all the main effects that go into that term. So what you do is you rule out certain possibilities. So this one here is typically ruled out by the fact that it's excluding a lower order term. Okay, a lower order term is excluding the main effects term for the factor. It's excluding that. And if you're going to include that interaction term, you probably should include the factor term, unless there was a good reason not to. Now you can imagine in certain things like a chemical reaction sort of situation, that would be a sensible thing to model to have. You've got no reagent, you expect no reaction. Okay. But generally speaking, what you would always include the lower order terms will fit the higher order terms. Otherwise, what you're doing is you're forcing an artificial constraint onto the way your model fits your data.
I mean, is it a general rule?
It's a very general rule. It's observed in the breach occasionally, but I mean, typically speaking, unless if you're going to fit a model, you fit one that includes all the lower order terms, unless there's a good a priori reason, something suggested by the science that something else should be the case. Okay, so when you're thinking about your experimental design, you typically think, well, okay, I don't have to allow for things like interactions between the blocking variables and the treatments, unless there's some sort of thing that suggests in the previous experiments that that's going to be an issue. So unless there's something in the previous science that suggests I should do this, then I don't. So what I do is I should, like most things, I should decide what my likely research analysis model is going to be when I do the experimental design, not after. And I stick to that as my reference model. Okay.
Can you go back to the receiver again?
Can I back up?
I mean, the plot? Sorry.
It's kind of hard.
Yeah, I just want to know, is it a pattern?
Oh, sorry.
So the way that you structure the workshops, is that done
Well, it's more to get you into the practice of doing those steps each time. Okay, so, and yeah, I mean,